So today in this talk, I would like to present a class of threat vectors against machine learning models known as adversarial examples, and tie back their mitigation with a set of fundamental challenges in artificial intelligence. Before I start, I'd like to thank the many collaborators who contributed to this line of work, including my advisor, Patrick McDaniel, and Ian Goodfellow from OpenAI, who helped me prepare this presentation. So in the previous talks of this session, we've seen the rise of AI. So machine learning is successfully applied to solve many challenging problems, such as autonomous driving or detecting financial fraud. Tudor showed in his talk how we can use machine learning to help detect malware and other advanced persistent threats. And more generally, there is a class of platforms who provide machine learning as a service to developers, such as Amazon and Google. And Dave, in the previous talk, he showed that an adversary capable of intensively querying the classifier and observing the score returned by the classifier can evade the classifier. So in his case, he considered the example of a detector for malware in PDFs. In this talk, I will consider a different application domain, computer vision, and I will show that a weaker adversary can target more complex models. Specifically, the adversary will only have access to the model through a remote API that returns the label assigned by the model and not the score. And the model itself can be much more complex with a more complex architecture like deep neural networks and many more outputs, up to 1,000. And the adversary is going to use something called adversarial examples, which are an instance of domain shifts. So we've seen in the previous talk, in machine learning, domain shifts occur when the training data and the test data don't have the same distribution. But with adversarial examples, what happens is the adversary is going to maliciously, on purpose, create this domain shift. And the adversary is going to create a worst-case domain shift to force the model to behave very poorly. So in 2013, a group of researchers at Google showed that they could use adversarial examples to force state-of-the-art computer vision models to make wrong predictions. And by doing so, they revived interest in a much older field of adversarial machine learning. So what you see on the left is a picture of a panda. It's correctly classified by a computer vision model as a panda among about 1,000 classes. And in the middle, what the researchers did is they computed a perturbation, which they multiplied by a small scale and added to the original image. And this produces the image on the right. And when presented with the image on the right, the machine learning model predicts that it's a gibbon with almost 100% confidence. Hopefully, everyone in this room still thinks it's a panda. So how did they do this? Basically, it's based on a technique that they introduced called the fast gradient sign method, which uses the loss function of the model. So during training, the classifier is going to use the loss function to estimate its prediction error and minimize it. And what the adversary does once the model is trained and deployed at test time is going to maximize the loss function. And is going to do so by first taking the gradient of that loss function with respect to the input, take the sign of this computation, and multiply it by a small threshold and add it to the original input. And the resulting input is very likely to be misclassified by the model. So one thing to note is here, the adversary needs to have access to the model architecture in order to define the loss function, but also to the model parameters to be able to compute the value of the gradients. And instead, in this talk, I will demonstrate how an adversary can conduct the same types of attacks based on adversarial examples and target black box models using something called transferability. So to make things clear, in this threat model, the adversary loses access to all of the following: the training data, the model architecture, the model parameters, and the model scores. Instead, the adversary has access to something called an oracle, which only returns the label assigned by the model for any input chosen by the adversary. So this corresponds to the scenarios that we discussed previously, such as models hosted on Amazon and Google's machine learning as a service platforms. It also corresponds to the scenario discussed by Dave of malware evasion, when the adversary is targeting an email service provider, and the adversary only has access to whether the PDF containing the malware was rejected or not. It cannot know how the prediction was made or what the confidence is. So we have two challenges here to perform our black box attack. We don't have access to the model. We don't have access to the training data either. So let's first take a look at the first challenge. We're going to use something called adversarial example transferability. It's a property that states that when you craft an adversarial example for a first model A, it's also very likely to be misclassified by a second model B. And this allows the adversary to follow this strategy. So first, the adversary is going to craft adversarial examples using the first model A, and then it's going to submit these same inputs to a different model B, which is the victim. And that model is also likely to misclassify the same inputs. So depending, to tie things back with Dave's talk, this would correspond to an adversary first interacting with a malware detector to find variants of PDFs that contain malware and are benign, and then submit them to a different malware detector, hoping that they would be misclassified as well. So depending on the pairs of models that you consider, you have many variants of transferability. So in this case, we have two models that are trained using the same machine learning technique, but on a different training data set. And we have what is called cross-training data transferability. If instead we consider two machine learning models that are trained using different machine learning techniques, but trained on the same data, then we have cross-technique transferability. So this allows the adversary, in this case, to interact with the deep neural network to find adversarial examples that evade it, and then submit these to a decision tree, which also misclassifies them. So you may be wondering, how is this likely to hold in practice? So let's take a look at a few experiments. On the left, you have an experiment conducted by partitioning a data set in 5 different subsets and training 5 logistic regression models, so one on each of these subsets. And then for each of the models, we craft adversarial examples and evaluate how likely they are to be misclassified by the other models. So on the y-axis is the model we use to craft adversarial examples, and on the x-axis is the model on which we evaluated them. So you can see that no matter what pair of logistic regression models we use, the adversarial examples transfer at least 95% of the time. If we repeat the same experiment with support vector machines, you can see the diagonal stands out much more, which means that an adversarial example is much more likely to be misclassified by the same machine, support vector machine on which it was crafted than a different one. And this is likely to be a consequence of the different mathematical functions used by the support vector machine, which force it to depend on some specific training points in some cases. And if we have a last experiment, the same setup, but with deep neural networks, then we can see something more intermediate with some rates that go up to 80, 70%. So now you may wonder, what if we use different machine learning techniques? So here we have cross-technique transferability. So what we did here is we trained a deep neural network, a logistic regression, a support vector machine, a decision tree, and a nearest neighbors. So they all solve the same task. We use them to craft adversarial examples that evade each of those models. And we evaluate how likely these adversarial examples are misclassified by the 4 other models. And so this is the same type of matrix where the y-axis is the model on which the adversarial example was crafted, and the x-axis on which it was evaluated. So you can see, surprisingly, despite the machine learning technique being different, there is strong transferability for a lot of pairs. And also, you can observe in addition that this property is not invertible. If you craft adversarial examples on a deep neural network, for instance, so the first row on the top, and you submit them to a decision tree, they are likely to be misclassified. On the other hand, if you do the opposite and use the decision tree to craft adversarial examples, they're much less likely to be misclassified. So then we wondered, what if we take an ensemble of models that take a majority vote using the 5 predictions of the model? And it turns out it doesn't bring much robustness compared to individual models such as deep neural nets or nearest neighbors. So this solves our first problem. We can use a different model to craft adversarial examples and then submit them to our target. But we still have a problem, is we don't have training data to create that alternative model called the substitute. So we're going to use something, a synthetic data generation technique, and here's how it works. The adversary starts by selecting a few unlabeled inputs, which are representative of the machine learning task solved by the victim. It sends these inputs to the victim, and the victim will return labels for these inputs, which allows the adversary to train a local substitute, which is performing very poorly because the adversary had very limited data to train it. So this is where the synthetic data kicks in. So we are using the Jacobian matrix to identify parts of the decision surface of the local substitute which have a lot of variation. And we query these synthetic inputs to the remote system, which returns additional labels, which we use in turn to update our local substitute and train it better. When this local substitute reaches a good accuracy, we can then use it to craft adversarial examples and send them back to the remote system. So in this case, we crafted a stop sign using our local substitute. It still looks like a stop sign to all of us, but the remote system classified it as a yield sign. So we solved the 2 problems. We don't need the model. We don't need the training data. So you may wonder now, how is this likely to work in real-world settings? So we conducted this attack on 3 remote platforms, MetaMine, Amazon, and Google, and we trained for each of them a substitute using the technique that I just presented. And after that, we crafted adversarial examples on these substitutes and sent them to the remote system to evaluate its error rate. MetaMine misclassified 84% of our inputs, Amazon 96%, and Google 97%. So you can see we have a strong success rate as an adversary against all of the systems. But if you look closely between MetaMine and Amazon, you can see we needed much more queries to attack MetaMine than Amazon. And the reason behind this is that MetaMine's attack decision surface is more complex, so we need more queries to get a good approximation of it as an adversary. So now, I would like to present a defense against such attacks, but also benchmarking efforts that I've been contributing to. So adversarial training is a defense that is very intuitive, and Dave started already mentioning it in his talk. Is basically you inject adversarial examples with the correct labels during training, hoping that your model will better generalize to them. So here's an example on a computer vision model where a model trained on clean data and evaluated on clean data has an error rate of less than 1% when training completes. And this is a model that was trained with adversarial training, with a mixture of normal and adversarial data. And it also has an error rate below 1% on clean, unmodified data. So now this is the error rate of the first model, the one only trained with clean data, on adversarial data. So we're crafting adversarial examples and evaluating the performance of the model. So it has almost 99% error rate on this data. However, the second model, which we trained adversarially with a mixture of clean and adversarial data, when presented with adversarial data, it performs with an error rate smaller than 10%, and during training it reaches about 2%. So this worked well in this case because the attack used by the classifier to defend itself and the adversary is the same technique to craft adversarial examples. However, if the adversary were to adapt its strategy, then this defense would not be very effective anymore. So this is the case for most defenses that have been proposed up to date against adversarial examples, and it remains an open problem. To help researchers and developers to benchmark their models against adversarial examples, and to help people deploy the defenses such as adversarial training to make their models more robust, I created jointly with Ian Goodfellow at OpenAI an open source library called Cleverhance, which you can download on GitHub. And as with all open source projects, we welcome contributions. So to give you an idea of how simple it is to use Cleverhance, here's a short tutorial. So the first 4 lines are basically defining a machine learning model in TensorFlow, which is a Python library. And then this model definition is given to Cleverhance in the line which is in bold, which automatically defines all the computational graph elements required to evaluate adversarial examples. And then the last few lines are measuring the error rate of the model on these adversarial inputs. So to conclude, I would like to tie back the mitigation of adversarial examples with 2 fundamental challenges in artificial intelligence. And so to make it simple, basically what we saw in this talk is that adversarial examples force the model to behave in the worst case settings. So we can observe how the model behaves when presented with worst case inputs. And being able to do so is a prerequisite for a set of challenging problems in artificial intelligence. Let me give you 2 examples. So there has been a lot of discussions lately about AI safety. These discussions are very hypothetical at this stage, but with adversarial examples, we can make them more tangible. For instance, if you're designing a driverless car with a machine learning component, you may wonder how is it going to behave in that one situation that is not in my training data, but that may occur in real life. And if you use adversarial examples, then you can force the machine learning model to explore these unseen situations during training data and see how it will react when explicitly provoked in the worst case basis. So our adversarial examples are a way to be able to trust the machine learning predictions. And this second example is model-based optimization. So if we were able to train a machine learning model that takes drugs and predicts whether they are very effective or not, then we could do model-based optimization, meaning we could use that model to backpropagate through it and find synthetic drugs that are very effective. The problem is that if we do this with the current machine learning models, then we're very likely to produce adversarial drugs. So drugs that the model thinks are very effective, but in practice, in the real world, are not. So again, the takeaway message is that if we want to be able to trust the machine learning predictions, we need to make sure that they are robust, the models are robust to adversarial examples. With this, I'd like to thank you for your attention, and as well as my sponsors for their generous support, and take any questions that you may have. Thank you.